Good morning, everybody, and thank you for coming. The conference will be focused on the consolidation of ornamental rocks and natural stones by means of carbonate creation. The finding is a result of a long research carried out by different investigation groups within the University of Granada, mainly the microbiology department as well as the mineral and petrology department where I belong to. This long research started in the mid-19th, and the most outstanding results have come out the first decade of this new century. One of those results has been the development of a patent. This patent has been raised to the interest of KBYO enterprise to its exploitation. In fact, KBYO is already developing the product to its commercialization and practical application. As introduction, we must understand which problem affects to build heritage, and once we understand it, we can find out the possibilities of intervention, preservation, and restoration. The interaction between a natural extractive material situated in a city center and different damaging factors like pollution provokes deterioration of those ornamental materials. It is known that pollution is a problem. It's not only a problem for our own health, but it's also a problem for built heritage. We could wonder, it really exists a cause-effect connection between air pollution and deterioration? Of course it is, and I will use the following two pictures to explain it. The left side shows an sculpture of a church in Ruhr-Batzin, the most industrialized area of Germany. The picture was taken in 1908. It means more than 200 years after its construction in 1702. On the right side, you can notice the awful condition of the same sculpture in 1969. Therefore, in 200 years' time, the sculpture kept in good conditions, and then, in just 60 years' time, the sculpture was deteriorated completely. The main reason is that from the first half of the 19th century, the Industrial Revolution all over the world, especially in Central Europe and in the British Islands, released a huge quantity of contaminants. Contaminants from the combustion of fossil fuels, coal initially and oil later. This type of contaminant damages ornamental material, deteriorates its appearance, vanishes all features like in this picture, and provokes the formation of the phenomenon called black crust, which is not exclusive of very industrialized areas. Granada, unfortunately, doesn't stand out for having an industry very developed. However, it doesn't exist pollution. We can see the formation of black crust in the Capilla Real and in the entrance of the Alhambra forest. We can notice an important deterioration associated to this kind of phenomenon. So, we will find in any environment, especially urban environment, an irreversible damage in any building caused by vehicle pollution. The alteration is not only produced by pollution. Materials can be degraded by other phenomena such as formation of black crust, other chemical processes, etc. There are also phenomena of physical alteration. One of the most popular is the crystallization of salt. The typical dampness that we see in the wall of both old and new buildings is produced by the crystallization of salts. The crystallized salts put pressure on the wall and roll the material and destroy it. People wrongly think that when the paint of a wall takes off, it's because of the dampness. Dampness is a gas, so it's not able to put pressure on the wall. Crystallized salts do put that pressure. These problems are important. Here we have an extreme case. It's Alcorbat in Cambodia. In this case, we have phenomena of physical and chemical alteration. These are rocks that grow up, press, and destroy part of the temple. In addition, there are other phenomena also biological. For example, the action of the microorganisms that cause biodegradation. So, we notice that the microorganisms can be a problem, but then we realize that these same microorganisms or other microorganisms specifically and controlled fed on can be the solution. Microorganisms can provoke biodegradation, and we will see later on that those same microorganisms will help to keep historical building efficiency and permanency. Here we have an example of biodegradation. This problem takes part in any part of the world where there are buildings of stone, mortar, brick, ceramic material, and so on. The solution is to recover the physical features of the material as much as possible. I mean, recover the cohesion, degree of integrity, mechanical resistance, and so on. How has this solution been implemented traditionally? With treatments of consolidation, refilling parts of the pores and trying to glue and protect the material. In other words, putting a superficial protection to avoid that damages penetrate inside the pores and continues damaging. These traditional treatments have been done with both organic and inorganic products. Organic ones have been used because of its versatility, easy synthesis, simple application, etc. For example, the case of acrylic resin known as the paradox of 72. Summarizing, organic polymers used to protect and consolidate. There are also inorganic products, for example, the water of lime. The water of lime is a classic treatment used since Roman times. Another example of inorganic product is the silicate that generates as gel silicone, quite popular in the conservation and consolidation of organic rocks. What is the inconvenience of these traditional methods? Most of the time, if we treat a stone with an organic material, what we are treating is an inorganic material. A stone is an inorganic set of minerals with its own porosity. If we apply on the stone an organic product with different physical and chemical features and different solubility, the main problem will be that the product doesn't penetrate enough and create a superficial layer. Let me show an example of what I am explaining. This is an acrylic resin applied on a porous limestone. The resin creates a film, like if it were a plastic on the surface. It prevents that the stone breaks. The consolidation is not deep, and consequently the treatment will fail. So we won't get the effect that we were looking for. and even worse, we will cause more damage. In order to avoid these problems of compatibility or inefficiency in the treatment, our laboratory simulated what nature does. How the nature creates a highly consolidated material. The nature can form a resistant and inorganic material through a biomineralization process. The biomineralization is the formation of minerals by means of mineralization of organisms. Bones, for example, are biominerals. They are mainly calcium phosphate and apatite. Another example of biomineral are corals, the cells of bivalve mollusks or archins with its skeleton formed by calcium carbonate. In many rocks exist remains of cells. They are easily visible inside the rock, and they are formed by calcium carbonate. Those minerals provide hardness to the rock. If we could regenerate those minerals in situ, we would get a consolidated rock with optimum characteristics. The handicap is that it hasn't been discovered organisms, such as mollusks or corals, capable to grow up and create a cell, a mineral structure in a modified rock. However, we find an organism called bacteria capable to create calcium carbonate by means of a biomineralization process. And in this process, we can see how the cells of those bacteria generate a type of cell which gets mineralized as calcium carbonate. If we have enough quantity of bacteria, we can create a kind of rock, a microbial rock formed by bacteria. Once we know that bacteria are capable to produce calcium carbonate, we can give them the nutrients they need to develop, multiply, and use its metabolic activity to produce calcium carbonate. As they are so small, they could enter in the porous system of the rock and consolidate that carbonate. The creation of carbonate by bacteria can appear because of the degradation of amino acids generating ammonia. Ammonia increases the pH, increases the medium, and creates a carbonate in presence of CO2, generated by bacteria or absorbed by the air. This carbonate, in combination with calcium supplied by us, provokes that those bacteria generate calcium carbonate. So, here we can see a new paste material that can consolidate a rock. This method of consolidation has been patented. Other proposals in 19 took the bacteria that generate calcium carbonate and were introduced in a stone to consolidate the rock. With this new method, we took the bacteria of the rock which are able to produce calcium carbonate themselves and provide them only the accurate nutrients needed. Not even one extra one less, in order to avoid the appearance of fungus or acids. The carbonate genetic bacteria receive what they need. In this case, we can consolidate the stone simply putting on a nutritive solution. All work is done by bacteria. We only supply the nutrients to activate them. Let's see some aspects of this treatment. Firstly, it must be proved if modified ornamental rocks have or not a microbiotic which can produce calcium carbonate, because we are not going to supply it any bacteria. The detailed studies, including select crops and RNA analysis, have identified the phylogenetic sequence of those bacteria that appear in different rocks, and have concluded that 90% of those bacteria can produce carbonate. We can see an example of how it is determined the capacity of producing carbonate. This is a colony of bacteria where are falling crystals of calcium carbonate in a capsule. This kind of crop can be made for any capsule which we will intervene. That is, we can determine if there are bacteria in this rock producing carbonate. As we have explained before, 95% of bacteria are carbonate genetic. These bacteria are not only in calcareous material, they are also in other comfortable environments. If bacteria are in an environment in which they can produce carbonate, logically they will also live in that environment. In the case of carbonated rocks, it has been proven that most of bacteria are carbonated. In other materials where we could think that these bacteria don't appear, they do appear. For example, in plasters. We will see an example of treatment in plasters works with the method of tactician in bacteria. The classic method, patented by French in 1992, consisted in applying bacteria to the material, then apply the nutrients, making bacteria grow up and carbonate it, and finally recalcifying the material. Our method omits this first part. We only add to the existing bacteria the crop with nutrients required for its development. How do we add it? Using a spray or a brush, depending on features. In this case, we have used the spray on the building, and we realized that results are excellent. We have noticed that this kind of treatment tested in laboratory showed good results in situ. We made tests both in laboratory and in different historical buildings to evaluate the efficiency of the treatment. Here we have the example of the external zone of San Jerónimo's monastery in Granada. It was constructed by a limey rock, where we applied treatment in some areas by pulverization of crop medium. In other cases, we applied even additional bacteria, and once the material is treated, it is covered. This application takes 7 or 6 days to keep it humid. Then it is covered to prevent a fast evaporation by the sun effect. After 7 days, we obtain results. How can we see or evaluate the consolidation carried out by those bacteria? Here we see the sample of sandy limestone before and after the treatment. In this case, we have used the technique of electron microscopy. This technique shows in detail the microtexture. We can notice here pores and crystals of calcium carbonate before the material treatment, a very cohesiveless and sandy material. And after the treatment, we see a whole material that recovers the stones and leaves pores opening. We also see cell remains of this bacteria. Everything else is calcium carbonate. It is a new material that consolidates against the material, as can be seen in tests by the simple and reduced test of stickers. This system consists in applying a sticker on a material before the treatment. When we strip off the sticker, we check how much sticker remains in the surface of the material. If we do it in many places, we will get a statistic of the quantity lost on the surface. After the treatment, we put again the sticker and check how much material is lost. It is quite similar to what any restorer does when he sees a material and he scratches it a bit with the finger. Here, we see quantitatively that the material before the treatment loses powder or superficial grains, and after the treatment, the quantity lost reduces to the fifth part. So, we can conclude that the treatment is very effective. Later on, we will see that there are other tests to evaluate the efficiency and to measure the resistance. Also, we can test in the laboratory the resistance to bath of ultrasounds to see how much quantity of material gets lost with this method. Before treating, here we see the big quantity of lost material, and after the treatment, the loss of material reduced a lot. The variations in the composition of the medium is another important aspect to consider. To get the culture medium eventually patented, we previously proved plenty of culture medium, each one with its own nomenclature, in 3, in 3P, medium CC, etc. The efficiency of the treatment can be evaluated with the bath of ultrasounds in treated and non-treated samples. The results show that non-treated samples lost a lot of material. In contrast, treated samples lost much less material until reaching that culture medium, which allowed more degree of cohesion. In this case, the kind of culture medium M3P gives the best result. Another very important aspect is the porosity of the material before and after the treatment. Normally, when the nutrients interfere, part of pores are refilled. So there is a reduction of porosity. This shouldn't happen. Pores shouldn't be plugged. By means of porosimetry and mercury injections, has been proved that the porous rocks with 29% of porosity after the treatment reduce its porosity in 1%. Regarding the pore size, notice in this distribution that green and red curves are superposed. This means that there are no significant changes. They produce consolidation, but it doesn't obstruct the pores. To optimize the treatment, we did geochemical controls to check the evolution of culture mediums once the nourishing solution has been applied. Observing evolution of pH, we see that when bacteria develop its metabolism, they increase its pH. pH can increase to pH highly alkaline. Regarding the calcium consumption, the calcium withdraws from the medium because it reinforces as calcium carbonate. We see that systematically, when we have bacteria activated by a nourishing medium, it increases the pH. And parallel to this increase of pH, we see that the calcium in the medium decreases quickly. In a control without bacteria, the quantity of calcium is constant, and the pH keeps constant as well, both because there is no activity that increases the alkalinity. The interesting thing is that after approximately 6 days, the rainfall of calcium is maximum. This means that after a week, the bacterial activity is not necessary anymore. All capacity of carbonates formation happens in the first week of treatment, which from the practical point of view is important because it means that this treatment can't be extended eternally. So, a week is enough for a standard and economic treatment. We see now an example of another material that doesn't have calcium carbonate in its composition. It's a plaster of L'Alcázar de Guadaira. It has been in an archaeological underground area. So there were elaborated and decorated panels, but very damaged. We carried out the treatment with bacteria. I mean, the activation of the carbonate genetics bacteria in this panel of plaster with this treatment patented. The appearance of the material before the treatment was crystals of plaster. Here we see an EDX analysis, and we see that the material has sulfur and calcium corresponding with the calcium sulfate of the plaster. The material got broken when you tried to take it because it was very porous and cohesiveless. The material also had a bit of calcium carbonate. The reason is that the traditional method didn't use plaster alone, but also plaster and lime to provide more strength. That's why it's very common to find a bit of calcium carbonate. The interesting thing is that calcium carbonate initially acts itself as hardener. This could compensate the calcium carbonate, which is generated in the bacteria and also act as a hardener. In fact, we see it happens. After the treatment, this is the surface of the treated material, all we can see with rounded shape. We don't see the small crabs of plaster anymore. It's all new calcium carbonate which consolidate the plaster. Inside, we continue to see crystal of calcium carbonate which covers the plaster. If we compare the results before and after the treatment using X-rays, we see that the formed material is basically a calcium carbonate. Here, we have the cycle of the treatment. The new polyformic of the calcium carbonate has almost the same power of consolidation that the calcite, a stable polymorphic. This treatment was compared with traditional treatments, traditional products like Movital, which is an organic polymer, lime silicone, or Paradoi, which is an acrylic resin of 1972. The inconveniences of these traditional methods are the formation of cracks, the pores plugging, and a non-homogeneous film on the material. But if we compare these old methods with the biotreatment, the most drastic effect appears when we do resistance tests to the drilling. It is a very simple system. Here, we have a drill that measures how much the bit penetrates in the material and the resistances to the cut. Newton gives us the idea of the hardness of a material in the whole piece, not only in the surface. All of us have ever made a hole in a wall with a drill. When you are drilling a hard part and suddenly you find a soft part, the drill goes deep inside very fast and easily. This phenomenon was measured in the three traditional methods mentioned before, and in the bacteria treatment in order to make differences. In this image, we can notice the results. From the surface to 1.5 centimeters of depth, the traditional treatment consolidates the first 3 or 4 centimeters maximum. However, our biotreatment, the treatment of bacterial biomineralization, consolidates the surface, and indeed that degree of consolidation is achieved in the whole profile. Why? Because the bacteria don't stay only in the surface. They are also living inside the material. If we activate these bacteria to create carbonate, we activate the bacteria of the surface and the bacteria of inside. That's why those bacteria generate carbonate in the whole material. And that is one of the best advantages of the method commercialized by KBYO's company, called KBYO Biological Enterprise. Thank you for listening.